Hi, here's a tutorial for a simply supported beam that's 8 meters long, supporting a uniformly distributed load, that's a UDL of 10 kilonewtons a meter. We're going to look at the deflected shape of the beam roughly, and then we're going to see if we can draw the bending moment diagram for the beam. Right. First of all, before we go any further, I think what I'd like to do is work out what the reactions are at each of these supports, so I can draw a free body diagram for the whole beam. So here's the beam, and these two reactions, they're going to be vertical reactions. Now there are no horizontal forces applied to this beam. It's got a pin support and a horizontal roller, so I'm sure that the horizontal reaction at this point is going to be 0, so I'm going to ignore that in my calculations. Now the total force applied to this beam is 10 kilonewtons per meter for each of the 8 meters. So big W is going to be 10 times 8, which equals 80 kilonewtons. So that 80 kilonewtons is applied over the full length of the beam. Now as it's symmetrical, I'm not going to waste time taking moments around each of the supports to find the reactions. I'm just going to use some common sense, and each of the reactions is going to be 40 kilonewtons. So if I resolve vertically, I have 80 kilonewtons going down and 40 kilonewtons going up at each of the reactions. Great. Let's have a little think about the deflected shape of the beam. Not much of a think, because it's a nice simple deflected shape, and that is it's just going to sag gently at its middle. That's it, simple as that. That's the deflected shape, approximately. What I want to do now is spend a little bit more time thinking about the bending moment diagram for this beam, because it's a bit of a complicated business working out this bending moment diagram, so we're going to have to do it in a number of small steps. So first of all, I've already split the beam up into 4 sections, so I'm going to work out the bending moment at 5 positions along the length of the beam. I'm going to work it out at A, B, C, D and E. That's right, it's an 8 meter long beam, so each of these sections are going to be about, well, exactly 2 meters in length. That's good. I'm going to draw the bending moment diagram. I always draw the bending moment diagram on the tension face of the beam, and I have to think to myself, if the beam's sagging down like this, which face is in tension? Well, I think it's the bottom side of the beam that's in tension, so I'm just going to draw a few T's along the bottom here to remind me of that. So when I put down the datum for my bending moment diagram, let's draw the datum here, I'm going to be drawing the bending moment on the underside of the beam. So if that's 40, I'll make that 80, make that 120. So just roughly 0, 40, 80, 120. I'm putting on a bit of a scale on the side for my bending moment diagram, which is going to be in kilonewton meters. Great. I'm going to start calculating the bending moment at various points along the length of this beam now. I'm going to start at A and E, my favourite positions, because the bending moment at a pin support for a beam that's not continuous across the end of the support is always 0. So MA equals ME equals 0, because that's the bending moment at the pins. 0, 0. Nice start. That's quick. Great. The next step in the calculations is to go to point B, and at point B I'm going to cut the beam and look to one side or the other. Now it looks to me as though if I cut the beam and look to the right, that's a bit more complicated than if I cut the beam and look to the left. So at point B I'm going to cut the beam, look to the left, and I'm going to draw out the free body diagram. That's A, that's B, and the whole thing is 2 meters length. So I've got a load of 80 kilonewtons a meter on the beam, of 10 kilonewtons a meter on the beam over a length of 2 meters. So I calculate that 10 times 2 equals 20 kilonewtons. So this load here is worth 20 kilonewtons, and I think it's acting at its centre, which is 1 meter from point B. That's good. So now I can take moments about point B and see what the bending moment there is. So if I take moments about point B, if I say clockwise is positive as usual, so 40 kilonewtons here, this reaction is acting 2 meters from point B. So 40 times 2, that's positive, because it's going to go clockwise around point B. That's point B. And then I also have the weight, or the force, from the UDL, the uniformly distributed load, which is 20 kilonewtons, acting at 1 meter's distance from point B. So the bending moment is 20 times 1. Now that would be going anti-clockwise around point B, so that's going to be negative. That's all the forces I can see, so I need to calculate that. That's now 80 minus 20 equals 60 kilonewton meters. Great, I can go to my bending moment diagram and just add that on. 60 kilonewton meters. Now I'm going to move along. I've done A, I've done B, now I'm going to have a look at C. C, I need to cut the beam and then look either to the right or to the left. Well, I'm going to look to the left because that's the way I seem to be working. So I'm going to draw out the free body diagram at point C. There, that's A, that's worth 40. That distance there is 4 meters away, and it's got a UDL acting on top of the beam, and I calculate that UDL is 10 kilonewtons a meter run times 4 meters is 40 kilonewtons. That's good. And the UDL is acting at its centre, so I reckon that is a distance of 2 meters from point C. Right, let's take moments around point C. MC equals, I've got the reaction at A, so that's 40 times its distance from C, which is 4 meters. And I reckon that is going clockwise around point C. And then I have the UDL, which has a total force of 40 kilonewtons, acting at a distance of 2 meters from point C. And I think that's anti-clockwise around point C, therefore that's negative. So add these two things together, plus 160 minus 80 equals 80 kilonewton meters. Great. Mark this onto my diagram, my bending moment diagram. At point C, I'm down to 80. And now I can go to point D. That's the only thing I've got left. Now ordinarily, at point D, I can cut the beam and look either to the right, which looks pretty easy to me, or I can look to the left, which looks a bit more complicated, but I'm going to stick with the complicated way because this seems to be the way we're doing it. Cut the beam, look to the left. We'll stick with that. You don't have to do that. In fact, if you're smart, you may say, this beam is symmetrical, therefore the bending moment at B and D is going to be the same. But let's do it by calculation just to make sure that we're heading in the right direction. So I'm going to draw out the free body diagram at point D. That's 6 meters, got 40 kilonewtons there at A, and I have the UDL, there it is, and that UDL is 10 kilonewtons a meter over a length of 6 meters, so it all adds up to 60 kilonewtons, and it acts at its centre, so the centre of the UDL, I reckon that is 3 meters from point D. Great. So now let's take moments about point D. MD equals 40 here, and that's at a distance of 6 meters from point D. So 40 times 6. That's going to go clockwise around point D, so it's positive. Then I have the UDL, which is 60, and that's acting at a distance of 3 meters from point D. And I think that would go anti-clockwise around point D, so that's negative. And so the whole thing adds up to 6 40s are 240, and 3 60s are 180, equals, what does that add up to? That adds up to 60 kilonewton meters. So let's add this onto my bending moment diagram now. 60 kilonewton meters. Now I'm going to do my best by turning this around to draw a smooth curve joining up these points, and it's going to be a curve because I've got a UDL along the length of the beam. So here's my curve, my best attempt at a curve. Not bad so far. There you go. And that curve, as it's a UDL on a simply supported beam, is actually a parabola. So whenever you have a UDL on a simply supported single span beam, you end up with a parabolic bending moment diagram, and it's drawn on the bottom because that's the tension face of the beam. And that's the end of that tutorial. Thank you very much for watching.